Right. It's my pleasure to introduce Professor Richard Shaughnessy from the University of Tulsa, who'll be talking about From Home to School, Tribal Indoor Air Quality and Intervention Study.
Thanks, Scott. Thank you for the opportunity to talk about our work. This is truly an applied study in terms of trying to help Native Americans and give them some information how they could help themselves in their homes and throughout different tribal nations in the U.S. But that's what I'll be talking about. I'm not quite coherent. I'm still trying to get over the U.S. soccer team not qualifying for World Cup. I'm in shock over that, and I'll try and get through it, but I'm thoroughly depressed, I got to tell you. So again, I want to acknowledge Jordan Peccia, the co-PI on this study. And the base study is related to was funded by the EPA, and the study design for that was to work with 104 families, Cherokee Nation, 12 schools, Navajo Nation, 14 families, 2 schools, and the Nimipu tribe, 28 families and 4 schools. And we had control and study homes that we were looking towards. Our objective was to look at asthma trigger source removal activities and targeted cleaning approaches as to the impact on symptoms. Tribal populations, I'm really not going to go into it, but Native Americans are disproportionately affected by asthma. Prevalence somewhere on the order of 25 to 30% higher than the general population. Certainly a population in need of being served, recognized. They are underserved as a whole, underfunded. Few studies come their way with respect to their population on indoor air quality, and they're highly protected. I mean, they're guarded as such. And so it's a privilege to be able to work with them, a true respect that we hold for them in having the privilege to come into their homes, and we took that very seriously. The hypothesis related to the EPA work as a whole was allergen reduction, improved cleaning, and education of occupants in both home and school environments can improve tribal and child asthma health. And as you might imagine, many diverse conditions, many different types of homes, low-income homes as a whole, many different types of activities going on in the home, so it was a wide cross-section of different types of homes, but primarily low-income homes. With that, as you might expect, all of the things that come with that, moisture, mold, failing conditions related to flooring, roofing, wood stoves are prevalent, much more in the northwest region that we worked in, pests and what comes along with that, and of course pets that they would have and what they would bring along with that. Exterior roof and siding issues, and so many failed building problems with respect to water intrusion and problems that they would have as a function of that. The Sloan supplement, or the overlay to the study, was focused on 2 environmental factors that may influence the indoor microbiome, and that being ventilation and cleaning. The hypotheses there were that increased ventilation will be associated with the shift of indoor air and surface microbiology to resemble outdoors. The second one was that cleaning surfaces will reduce microorganisms, but how will they truly change, or if not, the community structure of the indoor microbiome? And the third one, when we look at a crude indicator of, say, cleaning effectiveness, such as adenosine triphosphate, ATP, how does that compare with the organisms that are actually there? before and after cleaning. And so trying to compare that to DNA-based measurements prior to cleaning and post-cleaning. Ventilation is the first thing I wanted to go through. Just in general, ventilation, we've heard a lot. How many slides can you see of people sneezing over a couple of days? You know, you've got quite a few, but we understand ventilation to be important with respect to reduction of airborne transmission. Also, the other thing that ventilation in buildings, why do we have it? Well, for odor control, right? I mean, aesthetic purposes. And so, yeah, these are armpit sniffers. That's what they are for deodorant companies. And I like this because I'll show you here what we have here. We have the photo. I hate to take off time to do this, but we have the lady here, and that was a very old slide. Then I picked up one about 10 years later, and I am 100% convinced this is the same lady 10 to 15 years later in the same job, doing the same thing, which, again, I tell my students there's job security out there. You can look to this and see what we have. But what I want to talk about with respect to ventilation is tribal home ventilation and the effect on indoor microbes. So I'm going to show you, we took air exchange rate measurements, PFT measurements in a number of homes, and in doing so, you aren't looking at all the measurements here, but what you have are those, we dichotomized the top and bottom quartiles for the air exchange rate in the tribal homes. And what you have here is the ASHRAE 62.2 guideline of 0.35 air exchanges per hour as something to strive for residential settings. But gives you an idea of the distribution of what we have in the high and low ends of the study. In general, the summer ventilation rates had lower ventilation than winter. You might think that's strange, but very mild winters in the regions that we were looking at, primarily in northeastern Oklahoma, and in the summer extreme heat, so they close up more during the summer. And the observations from this are interesting in that, and I know you can't take all this in, but as we look across for PM10 and then break it down into bacteria and fungi, we see the distribution of at high air exchange rate, what the concentrations are, and low air exchange rate as well. And in general, after studying this, we see that the data appears to follow some sort of pattern, that being that bacteria, particulate matter, and fungi seem to be higher at a high air exchange rate. However, when we look at it further and we begin to look at the outdoor air concentrations, we didn't see that variance. In fact, the outdoor air concentrations don't appear to be linked to the air exchange rates or the seasons that we are measuring for indoors. The indoor concentrations do not seem to respond dramatically to changes in the outdoor air concentrations. And outdoor concentrations with season don't explain, in general, the indoor profiles that we see. So if we begin to look at our contributors to what we have for emissions, for sources, that is indoors, we look at the classic equation, we see, well, we have emission from sources, and then we have that which is contributed from ventilation. And these two combined give us our indoor source contributors. So in looking at each one of these, in general, and here's only an example of emissions rate data for bacteria, and you see that the emissions were significantly higher than that afforded by ventilation, which seemed to be the case across the board for the most part. As you see here, the ratio, the fraction contribution of indoor emissions approached unity in many of the cases, which again shows that that fraction is very important and makes up the predominant amount of the sources that we find indoors. Not so much affected, although we recognize it's affected by the ventilation, but the main contributor being the indoor activity, the emissions, what was going on in the space in these homes. And with that, the preliminary of what we're looking at right now, some of the conclusions are that the primary contributor to PM10 bacteria and fungi in the indoor air of these homes appear to be driven by indoor emissions, and not so much infiltration from outdoor ventilation. Then I want to show you the next part of the research, and that be our cleaning research. And in general, we take a step back. How do we define clean? And that's always a question that comes to mind. Are we looking at measurement? Are we looking at observation, the white glove test, or what? And with that, that's very important in terms of are we looking at residual contamination? And as Jack just showed you, and others as well, have talked about the importance of contamination in healthcare settings. There is little progress made against serious hospital infections. We know that clean may be better with respect to those settings, and greater than 2 million hospital-acquired infections per year. So what do we do? Well, to try and prevent these from occurring, we stress cleaner facilities and dealing with that, such to avoid staph infections, MRSA, things like that going on in the hospital. You can look to that preventive approach or deal with the resultant problem that I show you here. And these are, of course, treating foot ulcers. So if you don't want to go the clean route, you could always putting maggots on your foot to clean out the ulcer. I don't know if Jessica's here or Jack, but I love those graphics they have. I just love them, you know, how they move about. And if only I could get these to move about for you, maybe next time I'll get that to make a little more impact for you. But so I'm going to work on that. You know, when we're looking at trying to measure for cleaning effectiveness, we look at a crude indicator, ATP. It's an indicator of biocontamination. And it's a result of a reaction between luciferase enzyme and ATP, which is what fireflies, why they light up and such. But you have many of these on the market, many different monitors. And I don't have time to go into it, but this is a problem, that all the monitors are out there, but they don't give you the same readout. They don't give you the same range. They all seem to flatten out at the upper tier of the measurements. And there needs to be standardization with respect to the monitors themselves. However, we did look at this and using ATP measurements to look at what's normal on surfaces related to schools. Why schools? Because schools are a pit. They're disgusting. They're horrible. You know, I mean, it's just the way it is. If something could go wrong, it's not that it will go wrong. It already has gone wrong. And the conditions related to, sorry about that, overcrowding and ventilation and pets and everything crammed in there, and the inability to clean, even if you wanted to, are something to behold. And of course, you add children to that and all that we bring with it, and you've got quite an assortment of everything in there. And the only thing that really amazes me still about schools is that as a whole, as a society, we have the audacity to call these learning environments for our children and the future of our children's generations therein, which just astounds me. It truly does. And so the translation, I look at many schools in many different sites in different countries as well. And you see lack of clutter, clean, clutter-free, dry, cleanable environments, Scandinavia. And with that, you get a population that, you know, healthy, and they can learn and conducive to learning. But here in the United States, it's more like this. And with that, what do we get? Well, the result is more of maybe something to be desired in terms of, you know, the thought process and learning as a whole. We did look at schools and in 5 different regions, over 10,000 measurements on different surfaces within the schools in 5 regions of the U.S. And with that, we published on it, and what came out of it, you see this is kind of just an example of what we would find on ATP related to desks, cafeteria tables, bathroom doors, and bathroom sink areas. There are reasons why some of these are higher than others, and it doesn't particularly mean that cafeteria tables are more a problem. It depends upon the organisms, again, which is what we began to look into. But surface hygiene is important to student health, and more research is needed here. The conclusions from the series study, Cleaning Industry Research International, was that we were able to establish typical ATP ranges on different school surfaces, such that other schools and districts around the country can gauge where they are on a distribution of contamination with respect to what you might have in other schools across the country. ISSA, a cleaning organization, developed a K through 12 clean standard on that schools, and they are still working on that, getting that out there. As such, we're not directly affiliated with that, but they took our work and have adapted that to schools and their standard. And of course, again, surface hygiene is important, more research, and ultimately we're trying to get to improved health. The research questions that are important here is, can the research on the microbiology and the built environment point to surfaces that are more important to focus on? And so can we compare a crude indicator like ATP? What does it mean we get something high value, low value after cleaning? But what about the organisms that remain? Does that have any bearing? What are we actually removing when we're cleaning surfaces? Are we doing damage to the environment? Are we helping the environment? And so we looked at this further with the Sloan work. And we looked at 10 different schools, classrooms from schools in Connecticut. The desks were cleaned once. You had a pre-cleaning, if you will, and then we took post-cleaning samples. We took 24 hours, 3 days, 7 days, 21 days, DNA extracted from all samples, qPCR, and the samples were sequenced. Again, ATP and DNA sequencing, samples, swabs taken side by side, qPCR and the sequencing established therein. And this is essentially the kind of trends we'd get. Here you'd have for this some of the microbes, and you'd find ATP tracking that, which is very interesting. Now these are for desktops, keep in mind. But when we break it down, not just the sum total, it's still held true with respect to bacteria, fungi, and human cells, which again is very interesting. When we look at correlations between the ATP and bacteria, you had a correlation coefficient ranging from 0.9 for bacteria, 0.75 for fungi, 0.79 on human cells, and as sum total, 0.95, which is a good correlation. So not quite what we expected. We would have expected worse, but for desktops, this seems to hold true and is encouraging. In addition, when we look at this and we do pre-cleaning, and so we clean it, and then we look for the organisms to reestablish, we find that within about 3 days, organisms build back up on the surface. Okay? And as they build back up on the surface, that 3-day period is what we need to maybe look at more intensively. Here you have a heat map of organisms. Over here you have bacteria, and over here you have fungi. In the dark regions, all this kind of points out streptococcus and what. These are human organisms that are more important. So it's no big surprise based on what we found in the schools. As well, when we look at reductions after pre-cleaning, 1 day, 21 days, yeah, after 1 day, we do get reductions here, but they're not huge reductions, and then it begins to re-equilibrate after a period of time, as I showed you. The remark here is that on classroom desks, we found a good relation between ATP to bacteria, fungi, and human cells and the sum total. The ecology of the desk showed heavy influence of humans, oral, cavity skin. ATP tracks the reseeding of desk surfaces. It's in sync with qPCR results. And it also provides us the beginning as an indication of time necessary for the return of organisms, which really kind of interfaces with, if we're looking to clean for health, how often do we need to clean the surface as such? Tribal home progress, I'll try and wrap this up very quickly, is that, and that is with respect to the EPA results. We've trained, along with the Sloan work, we've trained many Native American students as to field researchers in 3 different regions of the country. Home and school measurements have been completed. Final analyses are still being conducted. And we're now translating all this into outreach for the tribes, specific to the tribes that we're embarking on in the next 8 to 10 months. So we're fully engaged in that. And this is the kind of thing we see. I mean, it's encouraging, again, preliminary results related to illness. What we find, there's been an increase in control homes, yet a decrease in study homes. Here, related to the gastrointestinal illness, we find this with respect to control homes, but with the study homes, we begin to find this curve, and that spike there has more to do with seasonal influences during the winter, which was occurring, where you have norovirus and things more prevalent. The challenges along the way is this, and this is with respect to MoBE as a whole. We're going to have bumps along the way. We recognize that. We try and fix the bumps. We try and forge forward. We look for research funding. We make this applicable. We make this useful. And with that, we try and figure out what those bumps are. We try to deal with the bumps, remove them. And as such, we change the design to go for a better design in the future. Our approach needs to change with that. Recall what we've done, change it, manipulate it for a happier environment for whatever we're working on. More healthy and happier people working together in the future. And that's a happier, healthier population is what we strive for. I wanted to thank the EPA, definitely the Sloan Foundation, Sealed Air Corporation, Charm Sciences, and SERI. So thank you very much.